I'm feeling good. I'm feeling locked in. I'm feeling like the pressure is on. This is right where I want to be. Crunch time, buddy. So today is about. So we tried to do some of this homework last night. It became very apparent to me that I was way in over my head, and I did not, in fact, know what was going on. So today is about special cases of these 2x2 systems. One where you have repeated eigenvalues, and the other where you have zero eigenvalues. Zero meaning, okay. In the previous 3 sections, we discussed linear systems y prime equals ay, for which the 2x2 matrix A has either 2 distinct non-zero real eigenvalues or a pair of complex conjugate eigenvalues. In these cases, we were able to use the eigenvalues and eigenvectors to sketch the solutions in the xy plane, to draw the x of t and y of t graphs, and to derive an explicit formula for the general solution. We have not yet discussed the case where the characteristic polynomial of A has only one root, that is, where A has only one eigenvalue. In previous sections, we also classified an equilibrium point as a sink, source, saddle, spiral sink, spiral source, or center, depending on the signs of the eigenvalues. Or the sign of their real parts. This classification scheme omits the case where 0 is an eigenvalue. In this section, we modify our methods to handle these remaining cases. Most quadratic polynomials have 2 distinct non-zero roots, so linear systems with only one eigenvalue or with a 0 eigenvalue are relatively rare. These systems are sometimes called degenerate. Nevertheless, they are still important. These special systems form the boundaries between the most common types of linear systems. Whenever we study linear systems that depend on a parameter, and the system changes behavior or bifurcates as the parameter changes, these special systems play a crucial role. All right, a system with repeated eigenvalues. Consider the linear system. So I'm just gonna, so this is section DE 3.5. All right, so if A is equal to minus 2, 1, 0, minus 2, and we form our characteristic polynomial minus 2 minus lambda times minus 2 minus lambda, that's it, equal to 0, then, right, when you see this upper triangular thing, you see that the determinant is the product of the diagonal if it's upper or lower triangular, I'm pretty sure. Anyway, so okay, all right, fine. So it's clear if you make the characteristic polynomial, like they do here, that lambda equals minus 2 is an eigenvalue whose only root is lambda equals minus 2. We say that lambda equals minus 2 is a repeated eigenvalue of A. We find the associated eigenvectors by solving A y0 is equal to minus 2 y0 for y0 equal to x0 y0. Okay, so then we turn, so since minus 2, lambda equals minus 2 eigenval, we solve A times x, y equal to minus 2 x, y. And then we can form equations. We can This is all, I'm doing this so repetitively because I'm realizing that I really need to do spaced repetition on this just so that I don't forget it in the quiz. So we can form minus 2x plus y is equal to minus 2x, then minus 2y is equal to minus 2y. So y is 0. Wait. Yeah. Okay, so 1, 0 is the eigenvector. So let's read that. Which yields y equals 0. Therefore, all eigenvectors corresponding to the eigenvalue lambda equals minus 2 lie on the x-axis. So all straight line solutions for the system lie on this axis. The vector 1, 0 is an eigenvector associated with lambda equal minus 2. And consequently, okay, wait, yeah. So then for initial conditions of form x0, we'll have the solution. This will be e to the minus 2t times 1, 0. But this is really going to be x. Okay, I'll be right back. Okay, but for other On the other hand, this is not a complete catastrophe. Our goal is to understand the behavior of the solutions of this system. Writing a formula for the general solution certainly helps, but this is not the only option. We can always study the system using numerical and qualitative techniques. To obtain qualitative description of these solutions, we start with one straight line of solutions. Because the eigenvalue is negative, we know that solutions tend toward the origin along this line as t increases. Looking at the direction field, we're using Euler's method. We can sketch other solutions Every solution tends to the origin as t increases. So we have a sink at the origin. For initial conditions that do not lie on the x-axis, it appears that the corresponding solutions make a turn and arrive at the origin in a direction that is tangent to the x-axis. These solutions look as if they're trying to spiral around the origin, but the line of solutions somehow gets in the way. In section 3.7, we see that the linear systems with repeated eigenvalues form the boundary between linear systems that spiral and those with two independent lines of solutions. All right, the general solution for this example. All right, so we have x prime equals minus 2x plus y, y prime equals minus 2y. dy dt is equal to minus 2y. dy over y is equal to minus 2 dt. We integrate and we get ln y is equal to minus 2t. So then we get y is equal to c e to the minus 2t. Let's call that c2 or something. So then if we plug in, we get x prime is equal to minus 2x plus c2 e to the minus 2t. And now this is let's get this set up. So oh wow, it's on. Damn, I gotta remember to turn this thing off. Really shouldn't be on. All right, so we're trying to find the general solution to this, and this is from a past chapter, but I need to remember how to do this. So we can use the guess and check method. And we'll do the bad guess because see how this is minus 2 and this is also minus 2? So first but I forget how you're supposed to do this. Like a linear system or linear DE is x prime is equal to ax plus b of t, right? Wait, is that right? No, that doesn't seem right. hold on. Let me double check in the book. We gotta, so this is section, this is chapter 1, man. So this is here. Actually, let's duplicate this tab. So, oh yeah. Oh yeah, no, okay. It's A of t, y, plus b of t. Okay, and then let's go to the guessing method. Yeah, I'm gonna need to do some serious review. Oh yeah, okay, wait. So if we go back, the first step is step 1. Find the homogeneous solution. So if we take x prime equals minus 2x, then we're going to get xh for homogeneous t is equal to e to the minus c. Let's do c1 e to the minus 2t. Okay, now that we have the homogeneous solution, we need to guess a particular solution, and that's where we're at. So right. No, okay, so what you have to do is then you move the y terms or the x terms, the dv terms to left hand side and solve, i.e. guess, for b of t. Okay, that makes sense. So if we go back, so we found this. So now we want to say that x prime plus 2x is equal to c2e. What the hell? c2e to the minus 2t. So now if we guessed that xp of t is equal to let's just say a e to the minus 2t, then we're going to get x prime p is equal to minus 2a e to the minus 2t, and 2xp is equal to 2a e to the minus 2t. But see how these cancel out? So this can't be our guess. So then what we do instead is we guess again. And we guess, so now we guess xp t is equal to a t e to the minus 2t. And then we get x prime of p, or x prime p of t is equal to, so then we have to do the product rule, unfortunately. So then we get a e to the minus 2t minus 2a t e to the minus 2t. and then 2xp is equal to just 2ate to the minus 2t. And then when we add these together, these cancel, right? So then we just get, we get ae to the minus 2t is equal to c2 e to the minus 2t. So then clearly all we need is that a is equal to c2. So then when we get the general solution, so the general solution x of t is going to be equal to our homogeneous solution, which is c1 e to the minus 2t. And then plus the particular solution, which is plus, wait. Is it really plus c2 e to the minus 2t? And then y of t is equal to c2 e to the minus 2t. Because the particular solution all right, so this is my answer, and I clearly need to review this, but that's my answer. So let's just check if we were right. So not this, but no, see, I did it wrong. How did I do it wrong? Oh, wait, you know what I think it is? I think you solve for A, but XP is still our guess. So this is actually C1. Wait, no, this is the guess. So this is the old guess. This is the new guess. So this is, but A is C2. So this is the particular, so we need a T in here. What's up, since like, okay. What's up, guys? Differential equations. All right, so let me just check if I was right. So y0. Okay, so we did get it right. Okay, good. Let me see, did I miss anything? No. Okay, so the general solution, we see that it's decoupled, and so we kind of get lucky. That's what they say, we kind of, and then we can guess a solution using the linearity stuff, and we get, so then, okay. So that was a little detour, but it was a good example. Now we study this solution closely to see if there's any pattern that can be generalized. If we separate terms that involve te to the lambda t from those that only involve e to the lambda t. So let me just write out the solution in terms of vectors. Y of t is going to be equal to e to the minus 2t times c1 and c2. plus te to the minus 2t times c2 and 0. Note that the first vector is the initial condition for the solution, that the second vector is an eigenvector. Oh yeah, the first vector is the initial condition, and the second vector is an eigenvector unless y0 equals 0. Okay, so if so this is the initial condition, and this is the single eigenvector. At first, the notation involved in the general solution may seem different than the notation we've used up to this point. However, we can think of the arbitrary initial condition as another pair of parameters. Rather than specify the general solution as a linear combination of two linearly independent solutions, we write the general solution in terms of the initial conditions. So this could be written as y of t is equal to e to the minus 2t of x0, y0 plus te to the minus 2t of y0, 0. Okay. For the case of repeated eigenvalues, this is the most convenient way to express the general solution. Okay, that makes sense. The form of the general solution. This form of the solution provides some hints on how to determine the general solution for a linear system with repeated eigenvalues. But only one line of eigenvectors. Okay, our standard linear system has a repeated eigenvalue lambda. Motivated by our example, we try to find a solution of the form. Okay, so this is y of t is equal to e to the lambda t v0 plus te to the lambda t v1. So this is like the form of repeated eigenvalue solutions or something. Okay, where v0 is our y0 initial condition. Given this form for y of t, we calculate both sides of the equation. For the left-hand side, we differentiate y of t using the product rule. For the right-hand side, we multiply y by the matrix A. This line I don't quite understand. Okay, so deriving or checking it's a solution. So we have y prime equals, so it's going to be lambda e to the lambda t times v0 plus e to the lambda t v1 plus, and then now the product rule, lambda t e to the lambda t v1. Okay, and they factor it, so this goes to, right, e to the lambda t times lambda v0 plus v1 plus lambda t e to the lambda t v1. Okay. For the right-hand side, we multiply y of t by the matrix. Okay, this is the left-hand side. Then the right-hand side is a times y. And y is equal to... Oh, yeah. Okay, so this is actually not that hard. So if you do a of... So I'll even show this on my thing. So if you have a of... So this is y of t. A times, and this just means times, e to the lambda t v0 plus t e to the lambda t v1 is going to be equal to e to the lambda t a v0 plus t e to the lambda t a v1. Okay, so that's actually not that hard. So the differential equation becomes, okay, so then we get e to the lambda t a v0 plus t e to the lambda t a v1 is equal to our left-hand side, which was e to the lambda t. Okay. Okay, so that makes sense. In order for this equality to hold, the e to the lambda t term on one side must equal the e to the lambda t term on the other side. And the statement holds for the t e to the lambda t. Okay, so then like we can group. Equating the vectors that go with the t e to the lambda t term. So if we like do this, this, and this, then we get t e to the lambda t a v1 is equal to lambda t e to the lambda t v1. So this means, oh, cool. So this is going to show that that v1 has to be the eigenvector, because we can cross out the t, so then we get a v1 is equal to lambda v1. Okay, and then our second part is going to be e to the lambda t a v0 is equal to lambda e to the lambda t v0 plus e to the lambda t v1. How can we, or I guess actually what we could do is we can cancel this, and then we get a v0 is equal to lambda v0 plus v1. The first equation says that v1 is an eigenvector unless v1 is 0. So v1 must be eigenvec unless 0. And the second equation says so then V1 is equal to AV0 minus lambda V0. But then we can rewrite this as, by factoring it out, we get A minus lambda I times V0. Wow. This strategy is actually really crazy. Okay, so in other words, the function is a solution if and only if V1 equals A minus lambda I V0 and V1 so this gives us a way to solve for V0, which is if A has so it seems as if the two conditions must be verified separately, but it turns out that if A has repeated eigenvalues and V1 is equal to A minus lambda I V0, then V1 is either the 0 vector or an eigenvector. If V1 is 0, we immediately know that if this is 0, then we immediately know that V0 is an eigenvector because that's what it means to be an eigenvector, is for this to be 0. Let me get my jacket. Okay, theorem. Suppose dy dt is a linear system in which the 2x2 matrix A has a repeated real eigenvalue lambda, but only one line of eigenvectors. The general solution has the form where V0 is an arbitrary initial condition and V1 is determined from V0. Oh, yeah, okay. So the theorem is if for y prime equal to ay, A has repeated real eigenvalue. And one line of eigenvec. Then the general solution is of the form y of t is equal to e to the lambda t v0 plus te to the lambda t v1, where v0 equal to x0, y0 is IC, and v1 is equal to a minus lambda I v0. If v1 is 0, then if v1 is 0, then v0 must be eigenvector. Evec. Okay, cool. Otherwise, v1 is an eigenvector. And why is that? Why must v1 be an eigenvector? Otherwise, v1 eigenvec. But why is that last part true? Don't make the mistake of thinking that the two separate terms are solutions. Remember, v1 is determined by v0. Dude, why do they always throw this freaking... Yeah, okay. If V0 lies in the eigenspace, then NV0 is equal to 0, so V1 is equal to 0. That is the straight line solution case. If V0 does not lie in the eigenspace, then V1 is non-zero. Now, why non-zero is an eigenvector? Compute NV1. Why is that true? Hold on. So NV0 is equal to V1. So NV1 is equal to N of NV0. That's fine. So you get N squared V0. Um, I don't understand. Bro, trigger warning. Trigger warning. I can't see the word kill. Wait. N has rank 1. So its image is also a 1D subspace, namely the eigenspace. That doesn't make sense. The kernel is the eigenspace, I thought. The null space of this is the eigenspace. Wait, let's just say I don't understand this part of it. The cur of N should be the eigenspace, right? Because you're trying to find vectors that equal 0. Why, bro? Why is N squared equal to 0? Dude, how does this book even explain this? What? I guess there's an exercise that goes into it. Because A has a single eigenvalue lambda of algebraic multiplicity 2, but only one independent eigenvector, its minimal polynomial must be that plugging A into that. Wait, what? See, I hate when it gives me stuff that's more advanced than I know. I don't know what a minimal polynomial is. Okay, well, maybe we should just keep going because it seems like there's going to be an exercise that we need to do anyways that'll get into it. Let's just read this last example. Okay, since A has a single eigenvector, call it V, we can extend V to a basis VW of R2. In that basis, think of it this way. Since A has a single eigenvector, call it V, we can extend V to a basis VW. In that basis, on the eigenvector, on the other vector, because no second, we can't satisfy that, but instead, it must be that. Oh, what? That's crazy, bro. Oh, that's crazy, man. Whoa, that's actually cool. Okay, so we'll get back to that for sure. All right, now let's keep going. In the example that we did by hand above, namely this, we found that we computed that lambda equal to -2 is an eigenvalue and that there's only one line of eigenvectors. So wait, we need to like categorize because like it's possible to have a matrix A such that it has, I think the way that they typically say it is that it has algebraic multiplicity 2. Wait. Algebraic versus geometric multiplicity. So algebraic, yeah, and geometric is the dimension. Okay, so basically what they're saying is, we can have, so in the case that there's, so just to write it down again, algebraic multiplicity is the multiplicity of the root in the char poly, the characteristic polynomial. Geometric is the dimension of the eigenspace, right? Yeah. Or cur of A minus lambda. Great. So this is an example. I don't know this Jordan block stuff. We haven't gone over that, but that's fine. Then and we haven't, I don't know how they get this TI thing. I don't know where they get that from. But anyways, then you get this and you figure out that there's a 1. Yeah, so x1 needs to be 0. Oh wait, no. This becomes x2 equals 0 and x1 is free. Okay, good. Yeah. Okay, so what is the case of 2 by 2 when we have 1D, or alg mult equals 2 equals G mult? So we have a 2-dimensional eigenspace and it has algebraic multiplicity 2. A is already diagonal. But for a 3 by 3, it doesn't have to be the case that every vector, it just has to be every vector in that eigenspace. So on that plane. All right, so let's keep going because we could spend it forever getting into the cool parts of this. Instant replay. In the example that we did by hand above, namely this system, we computed that we have one eigenvalue. So what this is saying is we have lambda equals -2 and only one, and this, the geometric multiplicity of this eigenvalue is 1. That's what this means, one line of eigenvectors. Following the method outlined in the theorem, we let V0 be the arbitrary initial condition x0, y0. Then we solved or we didn't actually do a solve, we just computed this thing. Okay, cool. All right, so this actually makes sense now. Last night when I was on my computer, I was not locked in. I was just trying to get it done, but now it makes sense. All right, the qualitative analysis of systems with repeated eigenvalues. Before discussing additional examples, we consider what the general solution tells us about qualitative behavior of solutions. The form of the general solution is this. We just went over that. e to the lambda t v0, where this is in the initial condition, plus t e to the lambda t v1, where v1 is either 0 or an eigenvector. The dependence on t comes in two terms, e to the lambda t and t e to the lambda t. If lambda is less than 0, then both terms tend to 0 as t increases. This is going to grow, but it's going to grow slower than the exponential at some point. To determine the direction at which solutions approach the origin, we factor out this, and we get e to the lambda t v0 plus t lambda v1. Since the directions of y of t and v0 plus t v1 are the same, we see that the tv1 term dominates if t is large. Thus, the solution tends to the origin in a direction that is tangent to the line of eigenvectors. Yeah, that makes sense, because this thing is going to go to 0 way faster than the t term. If lambda is greater than 0, then all solutions except the equilibrium solution tend to infinity as t increases, so the origin is a source, and the t e to the lambda t term dominates for large t if v1 is not 0. So what about the case when v1 is 0? v1 is 0 only if v1 is 0 only if our initial condition is on an eigenvector, I think. Almost positive about that. If we use the formula for the general solution to draw the phase portrait, we see once more that it looks as if the solutions If we use the formula for the general solution to draw the phase portrait, we see once more that it looks as if the solutions, other than the straight line solutions, are trying to spiral around the origin, but they cannot spiral since the straight line solutions get in the way. The usual form of the general solution of systems with one line of eigenvectors is another indication of the fact that these systems lie between systems with complex eigenvalues and those with real yet distinct eigenvalues. So where's our straight line solution here? This is the straight line solution. And they all end up being parallel to this thing, to this straight line solution. And similarly, they all end up being parallel. They said tangent, but I think parallel is a sufficient word. Oh boy. Okay, I'll be right back. Okay, so let's continue on. So a harmonic oscillator with repeated eigenvalues. Consider the harmonic oscillator with mass 1, spring constant 2, and damping coefficient 2 root 2. The second order differential equation looks like this, associated with its matrix form. The eigenvalues of this system, so let me all put it in my notes too. So we have consider harmonic oscillator. So we have y double prime plus 2 root 2 y prime plus 2y is equal to 0. As matrix, we get y prime is equal to 0, 1, minus 2 root 2 times y. Okay, and then we get lambda equal to minus square root 2 is repeated eigenvalue, eval. Given the eigenvalue, we determine the eigenvectors by solving yeah, so if we have like, well, it's really the kernel of that n matrix, which is it's b minus lambda I y is equal to 0. So if we have so it's going to be root 2 1 minus 2, and then it's going to be minus 2 root 2 minus it's going to be minus but plus, so it's going to be minus 2 root 2 plus root 2. But is that so then it's just going to be minus root 2 root 2 1 minus 2 minus root 2. Am I tripping? Am I crazy? Minus 2 square root 2 plus square root 2. This coalesces. Yeah, I don't know why. Sometimes you just see something and you're like, wait, am I dumb? Okay. So then we have this matrix, and we're trying to solve for the kernel. So we want root 2, 1, minus 2, minus root 2, x is equal to 0. See, how did they do this? They just did the matrix vector. I don't understand what they're doing here. So we could look at the equations and we could say that root 2 times y plus v is equal to 0. And then minus, here, I'll just show my work because I don't know what they're doing. So this is that n equal to a minus, or what do they call it? They call it b minus lambda I. So that's this matrix right there. And then we turn it into equations. We get this is going to be minus 2y minus root 2v is equal to 0. So yeah, so we're going to get that like v is equal to minus root 2 I'm pretty sure if we are these the same or not? Okay, they are the same. I don't know what I was doing. So then if y is 1, v is going to be minus root 2. So this is the eigenvector. This is the e-vec v1. Or actually, what do they call it? Do they call it v1? I think they do call it v1. Okay. So this makes sense. This line. For instance, one convenient eigenvector is 1 minus root 2. That's what we just did. The phase portrait for this system all solutions approach the origin as t increases, and all solutions are tangent to the line of eigenvectors as they approach the origin. To find the general solution, all right, so let's figure out the general solution. Let's do it without this thing. Let's just do it by ourselves because we're like that. Okay, so we have this system and we have it as a matrix. Now what we're trying to do is we just remember this, that that the general form, when we have repeated lambdas, eigenvalues, with where we don't have like a spanning eigenbasis. So so I'd say with one eigenvec, okay, is y of t is equal to, this is going to be something to remember. It's e to the lambda t v0 plus te to the lambda t v1, where, and this is going to be, I think it's v1 is equal to b minus lambda I times v0, where v0 is equal to y0 v0 is initial condition. Now, the tricky part here is, let's see, so, but we have v1, but let's just, so we have n, we're calling this n, and did we compute that root 2, 1, minus 2, minus square root 2, times y0, v0 is equal to these equations, right? So then we get root 2 y0 plus v0, and then I don't know if this is how we're supposed to do this. Okay, so they did do that. So they did do that. Okay, but this, for all points, is this guaranteed to be on the eigenvector? For the span of the eigenvector? This is going to be minus 2y0, right? Okay, so that's V1 in terms of the initial condition. All right, so let's just compute like a random point that's not on. Okay, so we know that the eigenvector is 1 minus square root 2. We know that this is the eigenvector. And then we know that the V1 is given by square root 2. I'm going to copy this because I'm going to type it a lot. Times y0 plus v0, comma, minus 2y0 minus square root 2v0. Okay, so this is the thing. And now let's just say y v is equal to I don't know, like 2 comma 2. This is not on the eigenvector. So then if we do v1 slash dot y0 goes to y, and v0 goes to v, then we get this thing. But is that thing in how do I check the last line is in the span of my eigenvector 1 minus square root 2? Check if. I think what I have to do is so let's just say this is foo. Oh. If we do foo divided by the wait. This is foo is equal to KEV. Okay, so I guess let me just clarify then. Are we guaranteed that the V1 Alright, so for this harmonic oscillator, expression in the first infinite, basically the b minus lambda I times initial condition, where IC is V0, that the V1 expert is going to give us something on the span of the eigenvector, no matter what y0 and v0. Why can't I see it? You know, what is it? Wait, b is equal to, okay. Okay, so whatever you give it, you are going to get something on the eigen. Okay. The eigenvector. So this is the general solution, y of t is equal to e to the minus square root 2t times, and this is going to be, y0 v0 plus te to the minus root 2t times this big expression, square root 2 y0 plus v0 minus 2 y0 minus root 2 v0. Okay, finally. We have so much stuff to do today. All right, Paul's and Bob's cafes one more time. Recall the model of Paul's and Bob's cafes from section 3.1. Suppose that the model has the form y prime equals ay, where a is equal to this. The coefficients imply that if Bob is making money, so the state vector, so x of, or let's say p of t and b of t, if b is positive, then Paul is going to increase. But if Paul is making money, then Bob's are hurt. In this model, coffee drinkers don't like tea. The eigenvalues for this system are the roots of the characteristic polynomial. There's only one eigenvalue, lambda equal to minus 4. Hence, the origin is a sink. And all solutions tend to 0, 0 as t increases. The profits of both cafes tend towards 0 no matter what the initial condition. To find the eigenvectors, we solve ax equal to lambda x, which has the line y1 equal to x1 as its set of solutions. From this information, we can conclude that as t increases, there's the straight line. As t increases, every solution tends to tangent y equals x. As these values of x and y tend to 0, they are almost equal. By looking at the direction field, we can see which initial conditions lead to solutions that tend to zero along. By looking at the direction field, we can see which initial conditions lead to solutions that tend to zero along y equal to x in the first quadrant, and which initial conditions end up in the third quadrant. Oh, wait, that's kind of weird. Because the solutions tend to the line y equals x, the two cafes have essentially the same profit and loss over the long term. The conclusion is a little surprising because the coefficients of the model imply that the profits of the two cafes react in very different ways. Effect of a small change in the coefficients. We might wonder what would happen if the coefficients were changed just a little. Suppose Bob decides that he will help Paul and puts up a sign. Are you tired of the tea party? Have some coffee at Paul's Cafe. I like that they threw that in there. The more people who come to Bob's Cafe, the larger Y is. The more the sign, it helps Paul. So the parameter B increases from, say, 1 to 1.1. The new system is this. The eigenvalues of this matrix are complex and have negative real part. Hence, the origin is a spiral sink. All solutions still tend to 0, 0, but they will oscillate instead of tending to 0, 0 along the line y equals x. This small change in the system has made a distinct change in the qualitative behavior of the solutions. All right, so they're priming us for bifurcations. However, the oscillations are very subtle. In fact, the phase portrait of x and t look almost identical. Yeah. Okay. All right. So that's good. Systems for which every vector is an eigenvector. At this point, we can discuss linear systems that have repeated real eigenvalues, but only one line of eigenvectors. An example of a system with repeated eigenvalues and more than one line of eigenvectors is given by this diagonal matrix with A as a repeated eigenvalue. Every non-zero vector is an eigenvalue, or every non-zero vector is an eigenvector. Even every non-zero vector is an eigenvector. Every vector is because the zero vector you're going to get. I'm pretty sure the zero vector is also. Oh, you know why? No, because we just by definition we don't consider zero vectors eigenvectors. Yeah. Okay. In this case, finding the general solution is equivalent to finding the general solution of the two equations. That is, the system completely decouples because every vector is an eigenvector. Every solution curve is a ray that approaches or leaves the origin as t increases. If a is greater than 0, all the tend to infinity. Otherwise, okay, so that's pretty simple. All right, this one I actually probably do want more help on. Systems with 0 as an eigenvalue. So we are trying to have a we are close to having a complete understanding of linear systems and their phase portraits. We can classify and sketch the behavior of solutions for the cases of real, complex, and repeated eigenvalues. The only case which we have not explicitly considered is the case where one or both of the eigenvalues is 0. This case is important because it divides the linear systems with strictly positive eigenvalues sources and strictly negative eigenvalues sinks. from those with one positive and one negative eigenvalue. Suppose we have a linear system and the matrix A has eigenvalues lambda 1 equals 0 and lambda 2 is non-zero. Suppose V1 is an eigenvector for lambda 1 and V2 is an eigenvector for lambda 2. Wait, hold on. What that means is AV1 is equal to 0. Right. So anyways, if you know linear algebra, you know that if 0 is an eigenvalue, then there's an if and only if with the matrix is not invertible and thus has non-trivial null space. I think the punchline here is that you get a line of equilibrium points, but I'll be right back. All right. Bro, I love streaming, man. Streaming's the best. I'm so locked in right now. All right. We have two real distinct eigenvalues, and all of the algebra we did in section 3.3 applies. So the general solution is, okay, so let me just say 0 eigenvals. All right, so for a system with lambda 1 equals 0, with V1 and lambda 2 not equal to 0 for V2, we have two real distinct eigenvals. So the general solution is going to be the sum of lambda I, or wait, the sum of e to the lambda I t times vi, or with k1, ki for constants. So then we get this, which is equal to, so we're going to get k1 e to the lambda 1 t v1 plus k2 e to the lambda 2t v2, but this goes to 0. Oh, wait. No. Sorry. This goes to 1. So we get k1 v1 plus k2 e to the lambda 2t v2. Okay, so note that k1 v1 term is constant, and therefore all solutions with k2 equal to 0 are equilibrium solutions. Note if k2 2 is equal to 0, then y of t is constant. Thus, equilibrium. You still need to find what that vector is, though. Okay, wait, hold on. If lambda 2 is less than 0, then the second term in the general solution tends to 0 as t increases. So it's going to tends to the equilibrium point k1 v1 along a line parallel to v2. Interestingly, though, it's not guaranteed that v2 and v1 are going to be orthogonal. So also v1 and v2 not necessarily orthogonal. So it's not going to like take the fastest route necessarily. Do we have a picture? So see here, it's like if v1 and v2 were orthogonal, then for any initial condition, you would be going as fast as you possibly could with as little travel to the equilibrium line. Okay, here's an example. Let's just do an example. So an example is, I'll do it on paper. Actually, hold on, let me move my camera forward a little bit. Okay, so we have y prime is equal to minus 3, 1, 3, minus 1 times y. So we make our characteristic polynomial, and we're going to get one hack, though, and they teach this in the next section, I think, is that you can do lambda squared. This is going to be, the trace is going to be minus 4, so we're going to get plus 4 lambda, and then the determinant is 3 minus 3, right? 3 minus 3, so this is going to be plus 0 is equal to 0. So then we get lambda times lambda plus 4 is equal to 0. So lambda 1 equals 0. Lambda 2 equals minus 4. All right, so we have our two eigenvalues. Now we need to find our eigenvectors. So we need to solve the system minus 3x plus y is equal to 0 and 3, because we're doing lambda 1, so this is for lambda 1. 3x minus y is equal to 0. So these are the same. Y is equal to 3x. So if x is 1, we get 1. 3 is the vec for lambda 1. Then if we do minus 3x plus y is equal to minus 4y, because this is written as a matrix, it's going to be ay equal to minus 4y. Let's put that in parentheses. So this is then 3x minus y is equal to minus 4v. Or wait, what am I doing here? X, y. I'm still thinking about the harmonic oscillator. Okay, so we're going to get y is equal to minus x and minus 3y is equal to 3x, so then y equals minus x. All right, it's the same thing. So then we get the other eigenvector is 1 minus 1. All right, so this is for lambda 2. Okay, so now we have our two eigenvalues and two eigenvectors. And I just want to draw a picture, maybe. Okay, so 1. Okay, so this is actually null of A. The kernel, or whatever you want to call it. And then we have 1 minus 1 here. And basically, so all these solutions are going to just tend, yeah, it's a negative, so they're going to tend in like this. They're all going to be coming in like this. Okay, now we still need to find the general solution. So our general solution is going to be y of t is equal to k1 times 1, 3 plus e to the minus 4t times, k2, 1 minus 1. There's our general solution. Now we can check if we got the right answer. They didn't even give us the general solution. All right, so I think we're ready to do some problems. All right, I say we do this the right way, and we just go hard. We just do it. Okay, so for these problems, we want to find the eigenvalue, the eigenvector, sketch the direction field. Okay, all right, so problem 1. Y prime is equal to minus 3, 0, 1, minus 3. Wow. Okay. So we get the trace is going to be minus 6, and the determinant is going to be 9. So then we get lambda squared plus 6 lambda minus, plus 9 is equal to 0. So lambda is a repeated, so we're going to get lambda plus 3 squared equal to 0. So lambda is equal to minus 3. And it's repeated, right? Because there's no other root. So it's a repeated root. So it's repeated. Now, let's see, what are the steps to solving this? One thing that we could do is we could go through this whole process that like x prime is equal to minus 3x, y prime is equal to x minus 3y, and then we'd find, we do this whole decoupled thing that we did earlier, which is like x of t is going to be equal to c1 e to the minus 3t, and then we have to do this whole thing where dy dt is equal to minus 3y plus c1 e to the minus 3t, and then we can figure out that the homogeneous solution of y is going to be equal to c2 e to the minus 3t. But then we have to guess our particular solution, so we guess that y p of t is equal to a t e to the minus 3t, and then we take the derivative of this, so y prime of p, or y p of prime is going to be equal to let's start with t is the derivative on this product rule, because we need to do the product rule here. So then we get ae to the minus 3t plus minus 3at e to the minus 3t. Okay, and then, oh wait, but did I do this wrong? No, so our equation becomes, because we move everything over, we get dy dt plus 3y is equal to c1 e to the minus 3t. And now all we're doing is we're solving this equation for a. And then when we do that, we're going to substitute back into yp. And then that will be our particular solution. And so then y of t will be equal to yh of t plus yp of t. Okay, great. So now we just need to substitute in here. And we're going to get this plus 3 this. So then we're going to get a e to the minus 3t is equal to c1 e to the minus 3. So then a equals c1. So then y of t is equal to c2 e to the minus 3t, because this is the homogeneous, this is yh, plus c1 e to the minus 3. Oh, wait. C1t e to the minus 3t. And this is yp. Okay. What's next? We need to so, and in this case, I think that the C1 and the C2 are actually the initial condition. So, but anyways, our solution is x of t is equal to c1 e to the minus 3t, and y of t is equal to c2 e to the minus 3t plus c1 t e to the minus 3t. And so we can write this as y of t is equal to e to the minus, or e to the minus 3t times c1 c2 plus t e to the minus 3t, 0 and c1. So this is our solution, but this is kind of the wrong way to do it. The way that you want to do it is different, because we know, we can just remember that so let's actually review the text again, because I need the repetition. So for the case of repeated, right, we take our initial condition. Okay, so the better way is 1, find eigenval, the eigenval. Then we know if one eigenvec that the general y of t is equal to e to the lambda t v0 plus te to the lambda t v1, where v0 is the initial condition and v1 is equal to a minus lambda I times v0. Okay, so let's just do that process then. So the first thing we do is we say let y0, or okay, let's just do it in their term. V0 is equal to x0, y0. Then v1 is going to be equal to a minus, and what is our eigenvalue? So it's going to be a plus 3i times v0. So a plus 3i is equal to 0, 0, 1, 0. So then we just need to multiply this by, so let's call this n. I don't know why I like that, but that makes sense to me. N times v1 or v0 is equal to 0, 0, 1, 0 times x0, y0 is equal to, and this is just going to be right? So this is v1. Yes. So then we can just easily say that y of t is equal to e to the minus 3t v0 plus te to the minus 3t of v1. So this kind of gives us a shortcut where we don't have to do this guess and check method or where for linear equations. Okay, so now what we want to do is we want to start to think about this geometrically because we're trying to understand the system, right? And the point is that, let's see, where is this line? This eigenvector is along the y-axis. Right, so we're going to have these straight lines here. And then we should... Now, I don't know which way they spiral. That's kind of the question. Do they go like this? Because they could go like this. So what I'm going to do is I'm just going to look at the derivative. So I'm going to look at a times 1, 0, which is going to be equal to minus 3, 0, 1, minus 3 times 1, 0 is equal to minus 3, 1. So at this point, x is decreasing and y is increasing. So it's going to go, I think, like this. So these solutions are like wrapping around like this. And then what that means then, but then what about like, probably these solutions too are like this. And then these solutions probably go like this. Oh, wait, is that true? No, 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 this is wrong. This is going to go like this way. So yeah, these come in the top, because if we took a of minus 1, 0, we would get 3 minus 1, right? So it here, x is increasing and y is decreasing. Oh, x is increasing, yeah, so it's going this way. Okay, so we were right. So it's wrapping around, and it's going to become tangent to this line. So, let's see. What else did we have to do? I think, oh, we have to find the particular solution. Let me go to the exercises. So we need to find the particulars. So, okay, oh wait, we need to plot the x of t and y of t graphs too. Okay, so this is the x of t, y of t graphs for y 0 equal to 1, 0. So what's going to happen is, can you see my graph? Probably not. Okay. Man, I wish this thing had better white balance. I need to just play with the settings because it's so dark. I mean, the shadows really don't help. But anyways, so we're going to start with x is up here and y is at 0. Y is going to go up and then slowly approach 0. Does it cross? I don't think it crosses. And then x of t is going to go like this, right? Okay, let's check our answers. Okay, cool. We actually plotted it pretty perfectly. Good. That's great. It's a good thing. It's a good thing. Okay, so let's switch back over and let's keep doing a problem. All right, so now we're going to analyze problem 3, which is y prime is equal to -2 minus 1, 1 minus 4 times y. So the first thing we're going to do is the trace of a, so this is a, the trace of the sum of the diagonal is equal to -6, and the det of a, the determinant, is equal to 8 minus -1, which is 9. Wait, 8 plus 1 is 9. So then you can always write the characteristic polynomial of a 2 by 2 as lambda squared minus t. So if this is equal to t and this is equal to d, then this is going to be minus t lambda, I think it's plus d. So this is going to be equal to 0, and then we're going to get the actual polynomial of lambda squared plus 6. Is that right? Plus d, or plus 9 is equal to 0. I think that's right. So then we're going to get lambda plus 3 squared is equal to 0. Lambda is equal to -3. So we have the same eigenvalue, but we don't and it's repeated. But one thing that's different is that this one is not lower triangular. So okay, so we need to find, well, since it's repeated, how do we know I think the case that if this thing had geometric multiplicity, meaning the dimension of the eigenspace for this is 2, then it would have to be it would have to be, like, I'm pretty sure that we can just tell that this has geometric multiplicity 1. But I'll be back in a second. Okay, I'm back. So we found the eigenvalue, and there's only one. So now what we know is that y of t is going to be equal to e to the minus 3t times v0, which is our initial condition, plus te to the minus 3t times v1, where v1 is going to be equal to a minus lambda I times v0, which is equal to, so this, I always call this n. n is equal to, so this is going to be plus 3, right? So we're going to get 1 minus 1, 1 minus 1. Okay, so then this times x0, y0 is going to be equal to x minus y, x minus y. So then our general solution should be y of t is equal to e to the minus 3t times x0, y0 plus te to the minus 3t x minus y, x minus y. So our eigenvector is the line y equals x. So if we're going to now plot this thing, we have this line here. Now what we want to know is for minus 2, minus 1, 1, 4, minus 4 times 1, 0. This is like my test point. We're going to get minus 2, 1. So this point out here is going to be decreasing in x and going up. So it's going to be going this way. So solutions are going to come in like this. And then similarly, we should get solutions that go like this. Okay, that's cool. What else do we need to do? We need to put the x of t and y of t graphs. So for 1, 0, y of t is down here, and it kind of goes up like this. So it's the same. It's the same thing. X of t, y of t. It's the same thing as up here, really. It just happens to be that the eigenvector is different. Okay, great. So we just did problem. Let's see, did we miss anything? We need to find the particular solution. So that's what we didn't do. So let's figure out what the particular solution is. The particular solution for these repeated ones is actually super easy because so particular for y0 equal to 1, 0. So all we have to do is y of t is equal to e to the minus 3t times 1, 0 plus te to the minus 3t times x minus y 1, 0. Oh, wait, 1, 1. 1, 1. Nice. And for up here, we get y of t. Y of t is equal to, so this is going to be this solution. What's interesting here is that what was n? N was this. So so that's why it cancels out to just be x0. So then I think this is going to be e to the minus 3t times our initial condition, which is 1, 0, plus te to the minus 3t times, this is going to be 0, 1, right? I think that's true because you just substitute in for x for what our initial condition is. So this x0 just is 1. All right, so this is the particular solution. I love looking at this. I don't know why, but this looks so cool. This like weird curved grid. All right, so we can now move on to the next problem. We're doing all of the odds. So we actually did just do 5 and 7. Okay, so what are we doing now? We are doing problem. So I don't really get what this one's asking, if they're asking you to do it again. But all right, so now we're doing number 9. Okay, given a quadratic, let me just write it down. Given lambda squared plus a lambda plus b, what conditions on a and b give? So part A is double root, and B 0 as a root. So let's hop over to this. Okay. So let's just do it. Lambda is going to be equal to minus a plus or minus the square root of a squared minus 4b over 2. If a squared is not equal to 4b, we get 2 roots. Now 0 is a root. So this is for part A. Now for part B, I think if A is equal to 0 and B is equal to 0. So we need A to be 0. But alternatively, we could have... If this is non-zero, then I don't think that we can... So I think that A and... Wait, that's not true, though. Because I know that we could do lambda... Okay, so if B is 0, so this is like the easiest one to find. So if A is non-zero, then we get minus a plus or minus square root of a squared, right, over 2, which is equal to minus a plus or minus a. So I think it's just b is equal to 0. Okay, let's double check our answer. So I think that's right. So this, of course, gives you 0 as a root, but then I think all you really need is b is equal to 0. And you're going to get at least, you're going to get one of them. All right, so let me duplicate this. Actually, let's just hints and answers. This is 3.5. Number 9. Yep, perfect. All right. Let's just read all these problems. So evaluate the limit of t e to lambda t is... Isn't it just infinity and 0? Why wouldn't it be just infinity and 0? I'm almost positive it's just going to be infinity and 0. Almost positive. Wait, what? For part B, use you get 1 over minus lambda e minus lambda t, which goes to 0. Okay, that one's fine. All right, problem 11. Did we do this one? Okay, so let's just do this one. So okay, so if it's gonna have two real eigenvalues, if if p squared is greater than 4q. B it states has complex eigenvalues, and that's going to be 4q is greater than p squared, and then part C has 1 eval, and that's going to be the condition that p squared is equal to 4q, because this goes to 0, and then you only have one root at p over minus p over 2. All right, that's problem 11. Problem 12. So they're gearing you up for the 3.7, but basically, why don't we do 12? 12 is good. So A is equal to A, B, C, D. Show if T equals A plus D and D is equal to AD minus BC. A has 1 eigenval if and only if t squared minus 4d is equal to 0. Okay, we'll switch over here. So a minus lambda times d minus lambda minus bc. We're going to get, this actually is going to get really messy, but that's okay. We get lambda squared minus a lambda minus d lambda plus ad minus bc. Okay, so we're going to get lambda squared minus t lambda plus d is equal to 0. And so then we have lambda is going to be equal to t plus or minus square root of t squared minus 4d over 2. And so if this goes to 0, then you only have one eigenvalue. So that is problem 12. Oh, problem 13 was actually really good. I did this one last night, and this is one of the few ones that I actually understood last night. So I'm probably not going to rewrite it down, but we'll go through it. So suppose A is equal to ABCD is a matrix with eigenvalue lambda such that every non-zero vector is an eigenvector. Okay, yeah. We're going to skip this one because I did it last night. All right, 14. Suppose lambda is an eigenvalue for the matrix, and suppose that there are two linearly independent eigenvectors, y1 and y2, associated with lambda. Show that every non-zero vector is an eigenvector with lambda, with eigenvalue lambda. What does this imply about ABCD? This is a really good problem. Okay, so I think I know how to do it. So let's do it. Okay, so this is problem 14. So we have A is equal to A, B, C, D, and lambda is eigenvalue. And y1 and y2 are eigenvecs. So ay1 is equal to lambda y1, and ay2 is equal to lambda y2, and y1, y2 independent. Okay? We want to prove every non-zero vec is eigenvec. Okay, so what we're going to do is just say y1 is equal to x1, y1, and y2 is equal to x2, y2. So we're going to get a, b, c, d times x1, y1 is equal to lambda x1, xy1. So this is going to be a x1 plus by1 is equal to lambda x1. cx1 plus dy1 is equal to lambda y1. So we get these equations, but then we also get ax2 plus by2 is equal to lambda x2. cx2 plus dy2 is equal to lambda y2. So we have both of these equations, and we're trying to show that we're trying to use these two sets of equations to show for arbitrary x, y that a y is equal to lambda y for all y. I'm less sure about how to do this one now. So, I mean, we have a minus lambda x1 plus by y1 is equal to 0. Cx1 plus d minus lambda y. I mean, I'm just rewriting the same thing over and over again. So I don't know how this is going to help me. Okay, well, if these are independent, okay. Here, if y1 and y2 are independent, then they form a basis of R2. So for some y, we can write y equal to, k1 y1 plus k2 y2. So then we just apply a to this. We get ay is equal to k1 a y1 plus k2 a y2. But this is equal to k1 lambda y1 plus k2 lambda y2. But then we can oh, okay, so here we go. Therefore, y is eigenvector. Yeah, see, sometimes you run around in circles and then you figure out, okay, let's just like think about what we're given and what does it mean. So very good. All right, and now the last part of this is, what does this imply about A, B, C, and D? That part I don't know. What does this imply about A, B, C, D? I mean, I'll say that like AC not equal to K BD for all K, but that's not what they want. All right, let's see. All right, so I got the proof part. Let's see what the last part is. So we did this and we found, okay, therefore every, oh yeah. Okay, wait. All right, I'm done cheating. All right, so since then we can write this a y is equal to lambda y for all y. Then this means that we can write lambda I is equal to a. So then if that's the case, then a is equal to lambda 0, 0, lambda. So that's the last part of that. All right. So it just implies, so it implies A equals D, B equals C equals 0. All right, that was a good problem, actually. I like those kind of proofy linear algebra ones. Okay. 15. Suppose two functions are equal for all t. Is this not just you set them equal to each other and then you say, well, this term has to be equal to this term? But actually, why is that? They say that in the book, but I don't know why that has to be the case. But anyways, then you divide by this, and then you create two equations, one where e to the lambda t w0 is equal to e to the lambda t v0, then you divide by e to the lambda t, and then you do it for the other side, and then you show that v0 equals w0 and v1 equals w1. Let's look at what their answer is. Okay, evaluate both functions at t equal to 0 and then any other value of t. All right, so t equals 0, this goes to 1, this goes to 0, this goes to 0, so then this. Now if you evaluate it at 1, you get the e to the lambda v0 plus, so let's just write that down. So at t equal 1, you get e to the lambda v0 plus e to the lambda v1, and the same thing, you're going to get e to the lambda w0 plus e to the lambda w1. Oh, and if you take it at t equals 0, then you get v0 equals w0. So then at t equal 1, e to the lambda v1 equals e to the lambda w1, and thus v1 equals w1. Okay, that one's pretty easy. All right, 16. Suppose lambda 0 is a repeated eigenvalue. Oh yeah, so we did this earlier. But it would be good to actually do that one again, because I feel like that one's really good. Given an arbitrary vector v0, let v1 equal to a minus lambda 0 I v0. Using the result of part A, show that v1 is either an eigenvector or the 0 vector. Okay, so you apply okay, so let's do it. DE 3.5, 16. Okay, so lambda 0 repeated for 2 by 2a. Show a minus lambda 0 I squared is equal to 0, the 0 matrix. All right. Okay, so how did we show this? We did this earlier and I don't remember. Okay. if n time nv is equal to 0 for some v, then v is an eigenvector. Let me see, did I miss anything in this? If we have a repeated eigenvalue, if repeated, sometimes I just write down stuff that I know and hopefully it works. If repeated lambda, then the characteristic poly is for a equal to a, b, c, d, and t equal to a plus d, and det and d equal to det a, then we get lambda minus t, lambda squared minus t lambda plus d is equal to 0. And we already know, since it's repeated, that t squared minus 4d is equal to 0. And since it's repeated, that means that we're going to get like the roots lambda is equal to, it's going to be t over 2. I think that's right, t over 2. So then we're going to get lambda minus t over 2 squared equal to 0 as our this is our characteristic polynomial. So if we had a minus lambda b c d minus lambda, and we took the square of that. If we just did this all out, a minus lambda b c d minus lambda, we do this big ass multiplication, but we're gonna get a minus lambda squared plus bc b minus lambda b minus lambda. And this is going to be I know this isn't the right way to do this. There's got to be a better way, but we're just trying to show that it's the 0, that this is the 0 matrix. So if we were to expand this out, we would get t is equal to a plus d, so we get a plus d squared is equal to ad minus bc. But but that doesn't show up anywhere, does it? Oh wait, does it? B times a minus lambda plus d minus lambda Similarly, we're going to get C, A plus D minus 2 lambda. There's got to be a better way to do this. All right, we need to thanks, man. Okay. How do we show that this is 0? Okay, so we were sort of on the right mark. Whoa, you guys got to see this. This is crazy, man. So I don't like that ChatGPT. I mean, in a way, it's actually nice that ChatGPT refers me to results that we haven't really covered, because then I feel like I have more experience. But since lambda 0 is a repeated root of the characteristic polynomial of A, then we have, and I don't know what this is, chi of A of t is equal to t minus lambda 0 squared. Cayley-Hamilton theorem says that a matrix satisfies its own characteristic polynomial. But read this though. A matrix satisfies its own characteristic polynomial. Is that not trippy as hell? Nice. A matrix satisfies its own characteristic polynomial. Dude, that's so sick. That's crazy, man. The Cayley-Hamilton theorem states that every square matrix over a commutative ring satisfies its own characteristic equation. Places say that characteristic polynomial is det of A minus lambda I, and others det lambda I minus A. Is it the same? Okay. This case 1 makes sense. Yeah, up to a sine. To the n? What is n? Oh, for an n by n. Okay. Interesting. Yeah, but it seems very beautiful. By replacing the scalar variable lambda with the matrix A, one can define an analogous matrix polynomial expression. The Cayley-Hamilton theorem states that this polynomial expression is equal to the zero matrix, which is to say that P A of A is equal to 0. That is, the characteristic polynomial is an annihilating polynomial for A. Whoa. Yo, that's crazy, dude. Why is that? That's so weird, dude. What are these coefficients? Where did they say that the coefficients are? In the characteristic polynomial, the coefficients the thing about the coefficients when it's bigger than 2 by 2 is that the determinant is crazy. Does it say what C is though? Yeah, let's look at 2 by 2. All right, so here we go. So this lambda squared minus, so this is our normal characteristic polynomial, except I want to quickly 1, 2, 3, 4. The difference between, so instead if we did 1 minus lambda times 4 minus lambda minus 6, we would get 4 minus lambda minus 4 lambda plus lambda squared plus 6. We would get will we not get lambda squared minus 5 lambda plus 10? So wait, they're not equivalent up to a sine though, right? Oh wait, why did I do A, B, C, D? I meant to do 1, 2, 3, 4. Wait. Am I stupid? Because I must have done this wrong. 4 minus lambda minus 4 lambda plus lambda squared minus 6. minus 6. Yeah, there we go. Okay, so I figured it. So this is going to be minus 2. So lambda squared minus 5, lambda minus 2. Okay, cool. All right. The Cayley-Hamilton theorem claims that if we define here we go. Here's the proof. Okay, so we were on the path of proving Cayley-Hamilton. That's sick. Wait, were we? No, not really. Not quite. But how did they prove it? Yeah, they did it using adjugates. That's crazy, dude. What if I drop Cayley-Hamilton in my quiz? Oh, shit. So in this case, we have to say a to the 0, right? Because this is going to be a to the 0. And the 0th power of a matrix, we do a is equal to AB, CD, and then we do matrix power A0. We get the identity. Okay, so that's why it's there. Okay, so show this is the wait, but why does this show that is the 0 matrix? We're actually not done. Yeah, let's read this thing again. I don't even understand this still. All right, let's read the non-Cayley-Hamilton proof. Okay, so n is equal to a minus lambda I. Case 1, the dimension of the kernel of n is equal to 2. In this case, then n of xy is equal to 0 for all xy. Thus, no matter what n is, then n of n is equal to 0. That's easy. Okay, case 2. Dim cur n equal to 1. Pick eigenvector v, then by definition NV is equal to 0. Since V is only one-dimensional, choose a second vector. Oh yeah, choose VW. Choose W, so VW is a basis. Now we write NW is going to be equal to, right, so they're independent. So we can write any, okay, so anyways, this linear combination spans R2. So then we can write that. So this is AV plus BW, since VW a basis. If B is not equal to 0, this goes to 0. Wait, what? How did they get this? Yeah. I'll be right back. Dude, the Cayley-Hamilton theorem is blowing my mind. That thing seems so deep. Why, bro, why would it satisfy its own characteristic equation? That's just crazy. But I want to understand this proof, because this is the proof that my book wants. Yeah. It's better to learn from YouTube. I agree, but actually, honestly, since this is just linear algebra, ChatGPT rarely gives me wrong answers. Okay, hold on. How did they get this? They did NW minus. Wait, what? Wait, what? Wait, why would AV go to 0? You look for a combination of W and V. Which is equal to, okay, which is equal to BW plus AV, which is equal to B times W plus. Oh, no, U. Oh, I get it. It's not 0, it's U. Yeah. It's not, yeah. Okay, so this is U because we set it equal to this. Hence, U is an eigenvector of n. So basically what we're saying is that n is going to project something onto its eigenspace. And then if you do it again, it's going to go to 0 because... Wait, hold on. It's going to project something onto the eigenvector of A. So n projects a vector U onto an vec of A, and since all eigenvecs are sent to 0 by n. All right, so I think that makes sense. Thanks, bro. Oh, so I didn't say bye. See you later, Mohammed. I don't know if you're still here. All right. Okay. Once you're in the eigenspace, n kills you, bro. Okay. Okay, wait, so let's go back to the proof. So okay, so we have NW is equal to AV plus BW. Is this an odd number one or even? Damn it. All right, I'm gonna do this, which is kind of lame, but I'm gonna do this. Just walk through the whole thing one more time. This problem is actually like crazy. Is a rank 1 nilpotent map whose image is exactly the eigenspace of A. I don't know why I'm having such a hard time understanding that. What's up, Sean? Okay, so what I'm trying to figure out is like, why is the image of n the eigenspace of A? All right, let's move on. Let's move on. I could do this literally all day, but this problem 16 is the best problem in this whole section for sure. It's not computational. It's like a very deep thing. All right, so let's just do 17 now. Get back to the. Okay, so we basically these problems you just do everything you can. Y prime equals to 0, 0, 2 minus 1. All right, so let's hop over to the camera. All right. Unfortunately, this the shadows are driving me crazy, but can't really do anything about it. Ugh. All right, whatever. It's fine. I'm just gonna keep working. All right, so we need to find the eigenvalues. So t is the trace is gonna be a plus d, so this is minus 1, and the determinant is gonna be ad is 0. The determinant is equal to 0. So the fact that the determinant is 0, you already know this thing isn't invertible. But our characteristic equation is going to be lambda squared plus 1 plus lambda plus 0 is equal to. So we're going to get lambda times lambda plus 1. So then our eigenvalues are lambda 1 equals 0 and lambda 2 equals minus 1. Right, so this is part A. Now part B is find the eigenvectors. So we need to find. So for lambda 1, we need to find 0, 2, 0, minus 1 times y equals 0. Okay, so if we write this out in equations, we get 2y equals 0 and minus y equals 0. And this gives us that y is equal to 0 and x is free. So the eigenvector here is going to be 1, 0, equal to v1. Now, for the other one, we're going to do, this is going to be a minus lambda 2I is equal to 0 minus minus 1. So this is 1, 2, 0. And this is going to be minus 2 plus 1 is minus 1. X equal to 0. So we got x plus 2y is equal to 0. And minus y is equal to 0. So y is equal to 0. Wait. Is that right? That seems wrong. I feel like I made a mistake. Wait, okay, let's just go back. So we have a times, say, v2 is equal to minus v2. So then we have a v2 is equal to minus 1 I v2 So yeah, so it's going to be 1, 2. Oh wait, how did this happen? Yeah, what? This is 0. Okay, so yeah, it was just a bug. Okay, that's fine. So we get x plus 2y is equal to 0, and 0 equals 0. So then we get y equals minus 1/2 x. So then we get our eigenvector is 1, or let's do 2 minus 1 equals to v2. All right. So in the case that there's a 0 eigenvector, so we can, in the case, so let's do a nice drawing instead of a shit drawing. Okay. So we have v1, v2. So 1, 0. So this whole thing, and this is lambda equals 0. So this whole thing are equilibrium points. And then we have 1, 2, minus 1. We have this point. Okay, so this is the other eigenvector, and what happens? What happens is, oh, that solutions are going to come along this way, and they're going to come like this. So they're going to go parallel to our set. So this is so these are parallel. It doesn't look like it, but they're parallel. And so now we need to find the general solution, right? So the general solution is we have two distinct eigenvalues. So we're going to have y of t is equal to, e to the 0t times 1, 0. This is going to be k1 plus k2 times e to the minus t, because lambda is equal to minus 1, times v2, which is 2 minus 1. But notice that this goes to 1, so then we get y of t is equal to k1 times 1, 0 plus k2 e to the minus t 2 minus 1. So this is our general solution. But now we need to find the particular solution for y of 0 equal to 1, 0. And in this case, it's at equilibrium. So then y of t is just equal to 1, 0. So that one was easy. That was easy to find. Oh, that was easy to find the particular solution, because we already had the initial condition is an eigenvector for the 0 eigenvector, so it's just going to go to 0. It's in the null space of A, basically. That's the easiest way to say it. It's in the null space of A. So we need to plot the x of t and y of t graph. So basically, this is already y of t at 0. So this is t, and this is the graph of y of t, and this is x of t. All right. So that's all of problem 17. Let's check our answer. Perfect. That's exactly what I had. Zero minus one. Perfect. And then the general solution was indeed this. And then this was, all right, sick. It's nice. Let's see. Okay, okay. Ooh, I actually want to do 21. 21 seems pretty cool. '22 seems pretty cool. I already did this one last night, so go watch that if you haven't seen that one. And then 24. All right, we're almost done with this. But this one has been a long one. 3 hours. Typically, it doesn't take me 3 hours to do one section, but last night I was like tweaking out how poorly I am. All right. I'm gonna skip 19. Let's do 20. Okay, so we're basically proving a basic theorem about determinants and eigenvalues. So, so we're trying to show. We're actually going to do an if and only if. So this is going to be the reverse implication that if the det is 0, then there's an eigenvalue that's 0. So B is actually easier, but let's show that. Okay, so let's let T equal the trace, which is A plus D, and D equal to AD minus BC. Then our characteristic equation is going to be lambda squared minus T lambda plus D is equal to 0. Now, if 0 is a solution, then D is equal to 0. So they're already, that's it. Our characteristic equation is, you know, I'm not going to do the whole expansion because I already did it like a bunch of times, but minus BC. If you expand out this, so this is the characteristic polynomial. This is chi of A. Anyways, you easily see that AD minus BC is going to be 0. So easy. Now we want to go the other way, B, and we want to show that if AD minus BC equals 0, then for, we can say this in a bunch of ways, but for non-zero V, AV is equal to 0. This one's actually the harder one, huh? Okay, so our characteristic, so if we know this, then our characteristic equation becomes lambda squared minus t lambda is equal to 0. So this is easy. So then we just do lambda times lambda minus t. Cool beans. That one was fun. I like those proof ones. All right. 21. Y prime is equal to 0, 2, 0, 0 times y. All right, so we want to find eigenvalues and sketch phase portrait. All right, so our characters, so t is equal to 0 and d is equal to 0. Then we get lambda squared is equal to 0. So lambda equal to 0 is the repeated eigenvalue. So wait, hold on. If we do 0, 2, 0, 0 times x, y, we're going to get for some point out here, it's going to go to this line, right? So I think the phase portrait is just going to be like, oh wait, actually, hold on. No, it's going to, I think it's going to be like this then. It's going to be like, dun, dun, dun. What if x is 0? If x is 0, or if y is 0, then it, so this isn't, right. So our eigenvectors, so 0, 2, 0, 0 times x is equal to 0. So we're trying to find the null space of A. So I think 1, 0. Yeah, so 1, 0 is an eigenvec. But then it does seem like that solutions go outward on x equal to 0. Oh wait, no, these stay. These are all equilibrium points. All right, should we look at the answer? 21. Oh shit. Oh yeah. Okay. I was trying to rush it. I'm dumb. Yeah, because this what I drew doesn't make any sense. No, right? Because if see, I don't know why I made that mistake. It's kind of embarrassing. If y is equal to 1, then there's an arrow going this way. Oh, I actually like this one. This one's cool. Okay. I understand it now, but I did flub it. Now B is just going to be the other way around. B is going to be, for B, it's 0, -2, 0, 0. And it's going to be arrows this way. This way. Okay. All right. The general solution. All right, this is the last problem. Let's just finish it, and then I can end the stream, and we can go on to 3.7. We're going to skip 3.6. I don't think we have any homework on 3.6. Okay, so 22, general solution. All right, of this. So we know that 0 is a repeated eigenvalue. We also found that 1, 0 is an eigenvector. Ooh, this is really good. All right, one sec. Okay, so what are we doing here? So, okay, intuitively, I can see that, like, if this is our matrix, then our equations are like x prime is equal to 2y, and y prime is equal to 0. Because that's just what that means. So we get this solution when we integrate this. And then we get x prime is equal to y 2y0, which is just a constant. So we get dx dt is equal to 2y0. So we get x of t is equal to 2y0t plus c. But that doesn't seem right. All right, I'm gonna just why is this 1 here? Oh, because y of t. All right, that's it. That's it for this section.